Welcome to this 10th and final lecture on material from undergraduate analysis, Math 4310 here at CU Denver. So this is on integration, and it corresponds to material from chapter 6, the final chapter in the Kenneth Ross book that I have been mentioning in all these recorded lectures. So this is a very sparse lecture. It's going to actually go by pretty quick. So the main thing that I'm going to do is present the notation so that you can see it, but rather than get bogged down in all the notation and the minutia of proving things, we're going to focus on the big picture and how a lot of results are connected, but we're not going to go all through all the results, and certainly not going to connect all the way to the fundamental theorem of calculus. You should read the book, or go to class if you're watching this as part of learning the material and see all these other things discussed. But we're just going to try to present kind of without all the complicating details how these ideas are connected, kind of the sequence of results that we get at, and the general way in which we have a perspective for proving these results. So, there's a whole bunch of material here that I've taken from the typed lecture material that accompanies these OneNotes, which accompany the recorded lectures. So you can also read that for some more details. But the thing that I want to emphasize is that the basic idea, the basic tool that we use is very much like a squeeze theorem applied to upper and lower estimates of the integral. And you might remember somewhat doing this from calculus, where you compute Riemann sums by taking a function and approximating the area of the curve in terms of the sum of the areas of rectangles with signed areas. And you could do like upper and lower estimates, and then you hope that as you refine your partitions, basically make the widths of your rectangles smaller, you get some sort of convergence. That's the basic idea. So the way we actually do this is we use what was called Darboux's characterization of integration. Eventually show it's the same thing as Riemann integration, but let's not worry about the details so much. It's really the same thing. So first, a bunch of notation just so that we can orient ourselves about what terms mean. And I've got simple examples, pictures to explain the initial definitions. So a partition of an interval a to b is simply a finite ordered subset of numbers. And it has the form a equals t naught, which is strictly less than t1, which is strictly less than t2, so on and so forth until you get to the final nth number, whatever that is, t sub n, which is equal to the right endpoint. So in pictures, it's something like this. If I have the closed interval a to b, then a is t naught, and then I just have this increasing t1, t2, and so on until I get to tn, which is my right endpoint. And so just the numbers are the partition. Now, the mesh of a partition P is simply it's a function that is acting on the partition. So really the mesh, I should maybe write it here, mesh of P is like it's a function that takes a partition as its input argument, and what it returns is the maximum length of any of the subintervals defined by the partition. So here's just an example where I show a partition T naught, T1, T2, T3, T4 of 0 to 1, and the largest subinterval defined by this is from T naught to T1, which has a length of 1/3. So the mesh of that partition is 1/3. That's that idea of a mesh. And then this next definition is really about more of notation. If we have a function defined on the closed interval a to b, and then we consider any subset, and for us, we're really going to be considering subintervals defined by meshes, we use the following notation. Capital M of f for s, M of f comma s, is nothing more than the supremum of f of x for all x in that set S. And if it's a little m, then we're considering the infimum. And if f was a continuous function and s was, let's say, a closed and bounded interval, then you could replace the supaninf with max and min if f is continuous. And I should say, and like, let's say s is a closed interval. That's somewhat important actually as well. So next couple definitions, you see there's a lot of definitions because there's just a lot of terminology and notation. Let f be a function on a closed interval. The upper Darboux sum, which is now capital U of f given p, and that's because it's defined with respect to a particular partition, is nothing more than this sum where you take this supremum of f on all these closed bounded subintervals, tk minus 1 to tk defined by the partition, multiplied by the lengths of that little interval, that tk minus 1 to tk. And for any partition, you clearly have that u of fp is less than or equal to this maximum value, or I should say the supremum of f on the entire interval ab times the entire length of the interval b minus a. If you don't see why, try drawing a picture and proving it. But here's the takeaway measure. Before we go on to definition in 6 and 7, let's just look at what this notation means. Given f, all right, this is what I'm writing over here on the right-hand side. U of f, like, and I put this little dot here as the argument, it's a function that maps a partition to a real number. So in other words, the idea when we're approaching integration is the function f is fixed, and we want to know if that function f is integrable. And the way we study it is we basically take a sequence of partitions, okay? Now, u of f for one partition might be different than u of f for a different partition. So the idea is that you can think of u of f comma as now having to replace what comes after that comma with the argument of the function. It takes a partition in and now returns a number through the process of taking this sum. So basically every partition is now gets mapped to a real number by this function u of f comma whatever that partition is. So if I consider a sequence of partitions, then it's actually pretty easy to show that if these partitions are just refinements, meaning that p sub n is contained in p sub n plus 1, because remember, a partition is just a set of points. So basically, if I add new points, all that I'm doing is possibly dividing, previous partitions into smaller partitions with the addition of new points, or previous intervals into smaller subintervals. So then what you end up showing is that this upper Darboux sum, you get a sequence of real numbers that's a decreasing sequence if you have such a sequence of partitions. And then u of f is simply the limit of this monotonic sequence, because we've shown monotonic sequences have limits. And so that kind of gives you a constructive way to describe how you build the upper Darboux integral and why it's defined in terms of an infimum over all partitions. Because as you refine partitions, basically you can only make the upper Darboux sum smaller. You can't make it larger. And then the opposite's true for lower Darboux sums. You basically take lower Darboux sums, and as you refine partitions, you can only make that lower Darboux sum larger, not smaller. And again, it's helpful to draw pictures. I'm not going to do it, but I basically want to make the point that what's going on is that as you consider a sequence of partitions that are refinements, L of f of Pn is a monotonically increasing sequence. U of f of Pn is a monotonically decreasing sequence. And what you'd like to see, like a squeeze theorem, is that the U of FPNs are coming down, the L of FPNs are coming up, and that what this number is in the middle is the value of the integral. So kind of pictorially, that's the idea. There's a whole lot of notation and terminology to get involved, but that's what we're getting at, all right? And we have to have like 7 definitions just to set up the terminology and notation. So then the rest of the results, I don't really want to dwell on them. I think you need to read them carefully. The short recorded lecture is really not the place to digest this. It's really about setting up all the results you need to show that basically there's no partition that ever makes a lower Darboux sum greater than an upper Darboux sum. All right, that's like one result that you need, is that kind of no matter what partitions you pick, you could throw any partition that you want at these lower Darboux sums, and they're all bounded above by an upper Darboux sum on any partition. And so that's what lemma 2 basically says right here. And what that means is that the lower Darboux integral has to be less than or equal to the upper Darboux integral. Again, I'm not going to go through the arguments for all of this. And so what we end up showing to show integrability of a function is that for any epsilon greater than 0, we can find a partition such that u of fp, that upper Darboux sum, minus L of fp, that lower Darboux sum, is in fact less than epsilon. That's one of these main results that we have. And another way that you might write that is with like Cauchy criterion using a mess function. And I'll just end here with theorem 3, which looks a lot like a continuity result because there's epsilon deltas, but we basically say a function's integral if for each epsilon greater than 0, there's a delta greater than 0, such that for any partition where that mesh function on P is less than delta, right? And P is this input to these functions that are the lower and upper Darboux sums for this fixed F, that you end up getting that U of FP minus L of FP is less than epsilon, which is very much like this theorem too. So, okay, that's it. There's a lot to take in. I didn't really go through any details, but the whole idea that you should really come away with is that we take upper estimates and lower estimates, and if we can show that the upper estimates minus the lower estimates for an integral can be made arbitrarily small, that difference can be made arbitrarily small, then the function's integrable. And it's basically based on squeeze theorems and taking like sequences of partitions in practice and using the fact that we have like monotonic sequences of numbers. So if you at least understand that, then you can read through the details and really take the time to do it carefully in the book. But I just want to give you kind of all these results and definitions in one place without a whole lot of complicating details. So, good luck, and I'll talk to you later.